My name is B. Ravindhar, Assistant Professor, Department of Electrical and Electronics Engineering, B.V. Raj Institute of Technology, Narsapur. Presently, I dealing the course on Power System 2, and the topic is types of insulators. So, what are the types of insulator we are using in a overhead transmission line? I'm going to explain about detail and what are the types of insulator we are using in distribution system as well as in transmission system. So first one we can see about the pin insulator, and second type is a suspension type insulator, and third one is a strain insulator, and fourth one is cycle insulator, and another is fifth is a stay insulator. So mostly insulator we are having, these are the 5 types of insulator in a overhead transmission line. Among these, the pin, stay and cycle type insulator are most common in case of distribution systems, and suspension type and strain insulators are used in case of transmission lines. So you can see that about this pin type of insulator, we can see in distribution system in our street also. So where this 3-phase transmission line, the 3-phase distribution lines is flowing, and it is having secured to the cross arms on this pole, and it is having a groove type of structure. We can see here it is a groove type of structure. At this groove upper end of this insulator for housing the conductor. So at this groove we can place the conductor, and for this conductor they can place at the bottom we have the pin, and it is placed at the cross arms. At the cross arm it can be fixed. So that is the thing we are having in case of this pin type of insulator. And this the conductor passed through this groove and is bounded by annular wires of the same material as the conductor. And we can see in this groove it is having the porcelain insulator. It is constructed by porcelain insulator, and it is having a cement cap at this case, and it is fixed to this pin. And at this bottom we are having the cross arms. So this one is the cross arms. At the top we can place the conductor. So like that it is there in case of distribution system, the pin insulator can be constructed. And this pin type insulator is employed only up to 230 volts and single phase, and 450 volt 3-phase supply. So this pin insulator is limited to applications like in a household application, like in our street. It is having if it is having a single phase, it may be connected pin type insulator, or maybe a 450 volts 3-phase systems. There you can see the pin type of insulator. And however, for 11 kV and 33 kV, the multi-seal pin insulators are provided. So if you go for 11 kV or 33 kV systems, this multi-shield pin type of insulator can be recommended for that, because this pin insulator can be not withstand for the higher voltage. So you can see that multi-shield means it is having a shield type of structure like this type of structure, and at this we are having the conductor is placed at the top like blue structure, and it is whenever the rain comes, this top steel at this structure it can be wet, and the bottom you can see this bottom structure it is a dry. So whenever there is a rain, this top structure can be conducted, but downwards it will be not connected, so that there is no leakage current pass through this pin. And it will be provided a longer path for the leakage current, so that magnitude of leakage current reduced and the physical size of this insulator is small. So that is the way we have this multi-shield insulator. During the rain, the top shield becomes the wet and bottom shield is dry, so that insulation resistance increase and magnitude of leakage current can be reduced. And magnitude of lightning voltage. So if there is a lightning comes, this lightning voltage is distributed among the seal, so the intensity of voltage reduction will be there in case of this multi-shield. Next disadvantage of this multi-seal insulator is if any one shield, so we are seeing that this is a seal type of structure like this. So if there is any one seal, this particular shield is damaged. If any one shield is damaged, we need to replace the total insulator. Okay, so that total insulation means this insulator is more costly. If there is a one this particular shield is get damaged. And the operating voltage increase, the cost of the insulation gets increased. So this cost is proportional to V power X, where X is greater than 2. For a voltage 66 kV and above, the string or suspension insulator can be used. So till now we discuss for 11 kV and 33 kV systems, we may use say less than 11 kV, means 230 volts or 450 voltage we are using pin insulators, and for a 33 kV or 11 kV system we are using a multi-shield insulator. And more than 66 and more than 66 kV we can recommend either a string or suspension type insulator. So you can see that next is the application of this single pin type insulator used to transmit the voltage up to 11 kV. So one particular pin insulator can be used up to 11 kV systems, and the higher voltage required 2 or 3 4-piece insulator. So we can connect in a series so that we can withstand for higher voltage also. And up to 33 kV used for transmission and distribution of electric power, and beyond 33 kV systems the pin type insulator becomes too bulky and hence uneconomical. So if you go for more than 33 kV, even though if you are recommending this pin type insulator, it may be bulky and the costly. So you can see the another type we are having is the suspension type insulator. So this suspension insulator we can observe here. See, in case of transmission lines, so the insulator is suspended like this, and this is the structure we are having. So this is a suspension insulator. Then we can see the one particular disc it is having. This type of disc arrangement we are having in case of this suspension type insulator. And this number of discs we can connect in series based on your operating voltage. So if you want to connect 66 kV or 132 kV or 220 kV, based on the transmission level of voltage, we can connect this number of discs we need to connect in a series. So this suspension insulator can be recommended for higher voltage greater than 33 kV. And it is usual practice to use suspension type insulators, and it consisting of number of porcelain discs connected in series by metal link in the form of string. So it is having through metal link, we can connect this insulator in a series. So, and it is suspended and supported high voltage transmission lines. So mostly used in high voltage transmission lines. And so cost, you can see they are cost effective for high voltage transmissions and typically replacing multiple pin type insulator. So instead of going say multiple pin insulator, we can recommend this series of suspension insulator. It is more effective. So this suspension type insulator have number of interconnected porcelain discs with each individual unit design to support a particular voltage. So this each disc having their voltage rating, so it will be recommended for the higher voltage, means we need to connect in series. So this we can see the cement cap suspension insulator. We have this type of structure, or maybe core and link type suspension insulator, and link or core suspension insulator, and third one is a interlinking or heavy suspension insulator. So these are the type of suspension insulator we have in the market. And this operating voltage, we can see for a 66 kV, how many discs we need to connect means. So this 66 by root 3, 66, 132, 220, all are line voltage. So we need to calculate in terms of phase. It is a line voltage divided by root 3. So that is 66 by root 3 by a factor 11 divide and plus 1. So you can get a 5. So in a 66 kV transmission line, we can recommend this suspension insulator. We need to connect 5 suspension insulator in a series. And if you go for a 132 kV line, it is a 132 by root 3, that is the phase voltage divided by 11 plus 1, then we can go for 8 disc. So we need to connect 8 disc in series. And in case of 220 kV line, it may be 220 by root 3 by 11 plus 1, then it is 33, and 400 kV line it may be 22, and 765 kV it is total number of disc are 35. So like that, we are having number of discs we need to connect in case of transmission lines based on their operating voltage. And the advantage of this suspension type insulator is cheaper than pin type insulator for voltage beyond 33 kV. So beyond 33 kV it is cheaper, and for each unit of disc suspension type insulator designed for low voltage usually 11 kV. and greater flexibility to the line, free to swing. So this suspension insulator, if you are designed like that, it is swinging very easily. Whatever the conductor we are connecting, it is freely, it can swing. But in case of pin insulator, it is not like that. It is not free to swing in case of pin type insulator. And increasing demand need to be raised the line voltage than to provide another set of conductor, a insulation required in this suspension arrangement by adding the desirable number of discs. So if your transmission line is designed initially in a 66 kV transmission line, later due to the demand increases, this line we need to extend to say 132 kV line, then we need to recommend that instead of one particular string, we need to connect a parallel string. Then we can increase the whatever the line capacity we can increase, even during this load gets increased. And as a conductor runs below this earthed cross arms, if the of this tower, this arrangement provides partial protection from the lightning. So this conductor is provided. This conductor is provided below that earth conductor. So earth conductor is at the top. At the downside of that, this suspension insulator will be there, so that we can protect from the lightning. And so you can see the another set of insulator we are having, that is a strain type insulator. So strain type of insulator. So if you see that this pin type insulator or this suspension insulator, if there is having a direction change. So if you are having a the transmission line is designed at say hill stations, or maybe at river crossings, or maybe at dead end. If you are having this suspension or pin type insulator, so there is more tension it will be developed at this crossing. So like this, it may be fall down this whatever pin insulator if you are having, or maybe a suspension insulator, it may be this tension will be like this. So we can't having a stable of this insulator. Then we are recommending the another type of insulator. It is called a strain type insulator. So this strain insulator, you can observe here, it is having the disc is like this, and it is the conductor is coming, and we are changing the direction. So changing the direction, there we can having the more tension at this location, then we can recommend this strain insulator will be designed like this. Or we can see that when the transmission this towers are having different height levels, then we can see the more strain is there. There we also we can design a strain insulator like this, and we can having the connection is like this. So you can see that dead crossing. So the transmission line is coming here, and it is changing its direction. In that case also we can use. So when there is a dead end of the line, or there is a corner or sharp curve, this line is subject to the greater tension. This dead end, or maybe level crossing, or maybe a direction change, there we are having more tension on this conductor. And in order to relieve this line of excessive tension, the strain insulators are used. For that case, we are having this strain insulator of arrangement. And for the low voltage lines, say less than 11 kV, these Sagil insulators are used as a strain insulator. So less than 11 kV. So whatever we discuss the strain insulator, it can be recommended more than 11 kV systems. That is our transmissions are 33 kV lines like that. And less than 11 kV system, we are having a Sagil type of insulator. Like in your street, if you observe, say 415 or maybe 230 voltage systems, where the dead end or maybe line crossing, or there is a direction change, there we are having this Sagil type of arrangements. And when the tension in the line is exceed high at a long river spans, two or more strings are used in parallel. So if you are having say more tension, if at that particular locations, instead of having a single strain insulator, we can connect a parallel of this insulator, so that we can withstand for the high tensions. So in this Sagil type of insulator similar to strain type insulator, and used on the shock cuffs, and end poles are in this section pole. So you can see that it is having this type of arrangement. So here the bolt can be fixed to the pole. It is having a pole distribution poles. It can be fixed onto this pole, and there we can connect a conductor like this. So we can see that whenever there is a crossing, means line changing, direction changing, then we can connect like this. So this is the arrangement we are having in case of distribution lines less than 33 kV about this Sagil type insulators. So you can see the arrangement of this Sagil type insulators are designed to support lower voltages and these insulators are single round porcelain part and they are mounted horizontally or vertically. So based on the requirements, it may be connected in a horizontal or vertical. And in early days, this second insulator was used as a stain insulator. In early days, actually, these suspension insulators are not in familiar. During that case, this stain insulator, this second insulator is used as a stain insulator. And they can be directly fixed to the pole with a bolt or cross arms. By the bolt or cross arms, they can be fixed to the pole. So you can see it is a shackle type of insulator. We are having this type of structure. Here we can connect the this conductor. So next, another type of insulator we are having, that is a stay type insulator, or you can also call as guy insulator or egg insulators. So where we can recommend this this guy or this stay insulator is that when the your distribution line is at dead end, and the transmission, whatever the this lines we are having like this, and at this case there is no mechanical support, so we are not having any support, so that it may be after say few years it may be bent like this due to this tension. So in order to relieve from this tension, we need to connect a support like this, so that it can be at any time it can be at stable location only. So for that we are having a one line is one particular wire, it is connected like this, and this particular wire, it is connected at the top of this pole, and it may contact with your cross arms, and in some days this particular pin insulator may get damaged, any one of the pin insulator, and then during that the current may pass to this cross arm to this line, and it is connected whenever there is a people or maybe animals which is comes surrounding to that pole, it may be die. So in order to protect from that, we have this insulations of this supporting whatever the line we are connecting, insulator is provided there. So stay insulators, also called as egg insulators, are primarily used to prevent the stay wires from becoming energized from the accidentally broken line wires. So when there is any accidentally, this pin insulator can be break, and there is a possibility of current can flow to this supporting wire. And the function of this providing insulation between this stay clamp and the transmission poles. And the stay insulators are mounted at a height at least 3 meters from the ground level. So from 3 meters onwards, so the people who are walking near to that pole, it may not be touched. So that clearance, it is required in that point of view. So these are the arrangements for this strain insulator. So another terminology we are having, it is called string efficiency. So what is mean by string efficiency? So this string efficiency is nothing but voltage across the whole string. So whatever the number of discs we are connecting, the voltage across the whole disc divided by string divided by the number of discs into the voltage near to the power conductor. So that is called the string efficiency. So if you are having a 4 number of discs, if you are connected in series, then the voltage across that disc are V1, V2, V3, V4, then we can calculate the string efficiency is nothing but V1 plus V2 plus V3 plus V4 divided by, so 4 disc, it is 4 into V4 into 100. And this particular string efficiency is less than 100% in case of AC transmission lines, and it is 100% in case of DC transmission line. So we can see that we are having the metal link like this, and it is having the 3 discs are connected, and we are having this equivalent of this particular structure is connected like this. So it is having the disc capacitance and also this shunt capacitance. These are the disc capacitance, and this one is called shunt capacitance. So these are the disc and shunt capacitance, and there is a current flowing takes place in this case. So what we are seeing that during the AC transmission line, this string efficiency is less than 100%. Why? Because due to this shunt capacitance. Due to shunt capacitance, we are not getting the string efficiency is 100%. But in case of DC system, we are getting string efficiency is 100% because we don't have any shunt capacitance effect. So for this derivation of this particular string efficiency, we have to apply the KCL at this point. So say point A, point B, point C. If you apply the KCL basic Kirchhoff's current law, so what is the Kirchhoff's current law is the algebraic sum of the entering current equal to leaving current. So here the entry current is I2 and leaving currents are small I1 and capital I1. So if you add like that at locations means at the node A, B and C. So we can get a three equations. We can see that at point 1 it is I2 equal to I1 plus I1 dash. Then you know that general equation of the capacitance current is equal to V divided by XC, and XC is nothing but 1 by omega C. From this IC equal to V omega C. IC equal to V into omega C. So for this case we need to calculate the current in case of I2. So this I2 current is nothing but this voltage. So here we are applying the voltage, this V2. This V2, what is the current we are getting? The capacitance current means I2 is nothing but V2 into omega C. So here C is there. So V2 into omega C is your the current in this case. Similarly, the I1 is nothing but this V1 into omega C. Here it is nothing but the same voltage, whatever the voltage it is appearing across this one, the same voltage appear across this particular shunt insulator. Then it is also V1. Then we are getting as V1 into omega C dash. Here KC. So we can see that it is omega C into KC dash. So it is C dash equal to K into C. So C dash is nothing but shunt capacitance. If you take, then it is K equal to C dash by C. So that relations if you apply, then V2 omega C equal to V1 omega C plus V1 into omega C dash, and this further if you simplify that omega get cancelled, then V2 equal to V1 into 1 plus K. So if you are cancelling this one, C dash is nothing but K into C. If you apply, then V2 equal to V1 into 1 plus K. Next, at KCL at point B, if you apply, then I3 equal to I2 plus I2 dash. And I3 is nothing but this current I3 is, so I3 means this particular current. This I3 is nothing but V3 into I3 into C, this capital I3. And this small I2 is nothing but, so you have to apply that voltage is, here it is voltage across this one is V1, voltage across this one is V2. So if you know unknown voltage is across this one, then if you apply the loop analysis at this, then V1 plus V2. So you have to add as V1 plus V2 is nothing but voltage across this current I2. So that we need to write here. So I3 equal to V3 omega C and I2 is nothing but V2 into omega C. This I2 dash is nothing but omega C dash into V1 plus V2. Then we can write further as V3 equal to V2 into 2 plus K. So if you write these relations, we can get this relation. Then V3 equal nothing but in terms of V2 is nothing but V1 into 1 plus K. And then finally we can get V3 equal nothing but V1 plus V3 equal to V1 into 1 plus 3K plus K square. Okay. And after this, we have to add these voltages V1, V2, V3. Then we can get as V1 into 3 plus 4K plus K square by, so what is the sting efficiency means V1 plus V2 plus V3 by this 3 into V3. Then we can get the sting efficiency. Then why this sting efficiency we are having this in case of AC system it is less than 10% due to the shunt capacitance effect, and there will be charging current in the shunt capacitance which will result as a current in the disc are unequal, so that voltage are unequal. So we can see that the disc we are connected like this. So we are connecting the disc like this. At this pin we are having the conductor and it is having cross arms. So due to this shunt capacitance effect, the current is not equal. So if there is no shunt capacitance effect, then the current will flow same current, then you can get the same voltage across the each disc. Hence, this current in this I4, whatever the near to a conductor is greater, I4 greater than I3 greater than I2 greater than I1, and similarly the voltage also which is near to the power conductor is highest. And in case of DC system, there is no effect of shunt capacitance, so the current in the disc are equal, hence the voltage are equal, and the sing efficiency is 100%. And then we have the multiplication factor C dash by C equal to K, and that is a multiplication factor. And C dash is always this shunt capacitance less than is very less compared to the disk capacitance, and then it is K is always less than 1. So what will be the effect of this string efficiency if there is a rain comes? So during the rain condition, we can see that insulators are wet. If the rain comes, the insulators are wet and the mutual capacitance gets increases, and the shunt to mutual capacitance decreases and the K gets decreases. This capacitance, whatever we are having, it gets decreased, and uniformity of voltage distribution gets increases. There is a more uniformity gets increases, and this string efficiency is having higher. So during the rain conditions, the string efficiency is high. Then we need to improve this string efficiency. Means there is the insulator which is near to the power conductor, it can develop more stress. We have to make equal distribution so that string efficiency can be improved. So what are the methods to improve the string efficiency? We are having, one is using longer cross arms and the grading of the insulator or the disc, and by gauge or grading of the ring. So we are having 3 methods to improve the string efficiency. So in order to achieve this 100% of string efficiency, or maybe near to means greater efficiency, we have the 3 methods in case of AC transmission lines. One is using longer cross arms, or maybe grading of the disc, or maybe by using gauge ring we can improve the string efficiency. So this method of this improving, first one you can see that using longer cross arms. So these are the cross arms. So if you are increasing this longer cross arms, one method, and another method is we are having the grading of the disc. So this particular disc we can having a different this capacitance, so that the grading can be achieved, and then also you can increase the string efficiency. So another method is by using this gauge ring. So at this bottom we are having a gauge ring, so that it can whatever the shunt capacitance current is there, that capacitance current can be nullified and make the efficiency can be greater. So that is by gauge ring. By using gauge ring or gauge, we can improve the string efficiency. So first method is we are having using longer cross arms. So during longer cross arms, so we are having a longer cross arm like this type of structure, it is there. And so it is a normal cross arms and it is a longer cross arms. So the length of this disc to this particular tower gets increased, then what will happen? The shunt capacitance is high during the shorter cross arms. So the shunt capacitance is high, so the C dash by C equal to K. Then C dash is high, K gets high. So the C dash is very less than C. The shunt capacitance is low. In this case, the shunt capacitance is low. For this case, the shunt capacitance is high. So using the longer cross arms, the distance between the insulator string, so whatever the string of insulator and the distance between this tower gets increases, then that as the distance increases, the shunt capacitance can be decreased. So the shunt capacitance can be decreased. As the shunt capacitance is decreased, the K value gets decreased. As shunt capacitance decreases, K value gets decreases. Then the K multiplication factor, it depends, and it is K approach to 0, then efficiency is near to 100%. Then we can increase this string efficiency. So how you can improve the string efficiency using longer cross arm is, as the longer cross arms, the distance between this disc suspension insulator and this tower gets increases, then shunt capacitance effect get decreased. As the shunt capacitance decreases, K value decreases. As the K decreases, the string efficiency can be improved. So like that we can improve the string efficiency by using longer cross arm. But what is the limit of this using longer cross arms? And there is a limit in increasing the length of cross arm due to the economical consideration. So if you are going this longer the cross arms, the structure it is required, the transmission line is more, then it is not economical. Next is grading of the insulator disc. So we need to grade the insulation disc So it is having the conductor. So first top one is having a capacitance C1, next disk is having a C2, next another disk is having a C3. So it is having different capacitance C1, C2, C3. So for equalizing the voltage distributions, the minimum capacitance which is having the disk is placed at the top of the tower or near to the tower, and the maximum capacitance of the disk can be placed at the power conductor. So disk of different dimensions, we need to see that V is inversely proportional to the capacitance. So you can see that we are making the voltage distributions are equal, V1, V2, V3 equal to V4, then corresponding voltage drop is nothing but this current is nothing but I1 into XC1, I2 X2 like that. Then currents are less at the top of disk and highest at lower disk, and corresponding capacitance you can see that higher at the power conductor and least at the top of the tower. So like that we can make the grading of the insulator. If the disks are non-uniform, the mechanical stress in the string is uniform. So mechanical stress in the string gets uniform if the disks are non-uniform. And so the given string has become brittle, hence the grading of the disks are not recommended. So these are the disadvantages of this if you are recommending the grading of the insulator. If the disks are non-uniform, mechanical stress in the string is uniform, and so that the given string has become brittle and the grading of the disk are not recommended. Next, for this calculation of the capacitance of this each disk, how we can calculate the capacitance for this particular disk, we have to apply the KCL at this point here, and previously whatever the string efficiency we are calculating, the all capacitance are C only, but now it is a capacitance C1, C2, and this capacitance we are making as C3. So that C1, C2, C3 different capacitance we are the disk we are constructing, so that we can make the string efficiency can be improved. So at that point here, if you are applying KCL, then it is I2 equal to I1 plus I1 dash, and then corresponding V2 equal to V1. And then it is if you are making this C2 equal to C1 plus C dash, you can get at point B. If you apply KCL, then it is I3 equal to I2 plus I2 dash, and I3 is nothing but V3 omega C3, and this I2 is nothing but V2 omega C2, and I2 dash in this case the V1 plus V2 is the total voltage appear across that, and omega C dash. And this case the all voltages are equal, then V1 V2 equal to V3, and if you make then C3 equal to C2 plus 2 into C dash. Here V1 plus V2 means 1 plus 1, it is 2 into C dash. Then similarly means for n number of disks, the Cn equal to Cn minus 1 plus n minus 1 into C dash. It is a general equations, the number of disks we need to connect, and it's the capacitance value based on this how many strings these insulators are connected particular string. Next, another method we are having use of grading ring or static shielding method. So guard ring or guard ring is basically a metal ring which is electrically connected, this grade ring, to the conductor surrounding the bottom unit of the string insulator. So there is a metal ring like this, it is structure is connected, which is connected at the bottom of the string insulator. At bottom of the string insulator we can connect this particular ring. So the guard ring is introduced the capacitance between the metal link and the line conductor, which tends to cancel out the shunt capacitance. Whatever the shunt capacitance effect you are getting, that capacitance get cancelled, so that we can improve the string efficiency. So as a result, nearly same charging current flows through each disk and improve the string efficiency. And grading insulator ring are sometimes similar to the corona ring, but they are encircling the insulator rather than conductor. So through this this particular insulator it is connected, but this corona ring it is connected like this, means it is connected to the conductor. Now we are having a disk, it is having this disk. This is like this type of ring it is there. That is the case in case of this grading ring. And due to this static shielding, there will be another capacitance between the string of insulator guard ring, and which is called static capacitance. So we have the shelf capacitance, means a disk capacitance, then it is having shunt capacitance. Another capacitance it is exists between this your means guard ring and the disk, it is a static capacitance. And due to this static capacitance, there will be a charging current which are equal to the charging current of the shunt capacitance. Hence, the current in all the discs will be same and the voltage are equal. So the string efficiency is 100%. So what we seen that there is a disc is connected like this. And it is having a power conductor. In this case, we are having the this particular capacitance is like this, and it is a disc capacitance. So if you are having another capacitance from this, and it is having God ring is like this, so that this capacitance, so this capacitance and this capacitance are equal, so that these currents can be cancelled out, so that we can improve the string efficiency. So mostly the same current will flow from top to bottom, so the voltage distribution will be similar, so the string efficiency can be improved. So you can see this is the insulator, this grading insulator rod ring or grading ring. It can be connected surrounding the insulator. So this is the grading ring. So we can see the transmission lines, how they are connected like this. And disadvantage of this grading ring is the grounding method will be provide equal voltage among the disc and also protect the string of insulator against the direct lighting, and it is called as ineffective method. And if operating voltage is high, so say like 132 kV, 220 or 765 kV, like that, the number of discs gets increased, so that there will be a number of longer length of the string and the length of the guard ring is also long. So longer guard ring is required for that case. Hence it is very difficult to have the longer length of guard ring. Further, there is a failure of this guard ring will create a short circuit in the system. Hence practically it is difficult to have the static shielding method. However, the string of insulator is protected by having earth wire on the top of the tower. So at the top of the tower, it is protected by using this earth wire. So today we discuss about the type of insulator and what is the string efficiency and what are the methods of string efficiency we discuss today class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.